All right, good morning. All right, good morning, everybody. So how's everyone today? Cool, good to hear. I'm doing good too, thanks. All right, any questions from what we've done so far? Everybody who has done the quiz has gotten 100%. Awesome job. But about 15% of the class hasn't done the quiz, so putting it off. Yeah, we read the syllabus and we found out that this is CSE222, which is the key to nailing that quiz and making sure you know you're not in Scuba 101 or basket weaving. And yes, SLP thing, and I will read that over and give you some feedback this afternoon. Basket weaving and programming are kind of the same thing. It's starting small and you have a few basic operations and you're trying to make something, you know, large and freestanding out of that. So kind of like assembly language programming. All right, let's talk about, underwater basket weaving was always the thing we talked about in school. So yeah, scuba would work. Let's talk about data. So this is a data structures course, right? And if we think about data a bit, you know, computers have basically instructions and data. And the instructions specify certain things we want to do to analyze or manipulate the data. And the instructions themselves can be, you know, treated as data, and data can be treated as instructions, and so on. But let's think about C. Running on, you know, whatever your favorite processor is, and what types of data can our C program work with? So what are some of the data types that we have? And you can either use the chat window or open up your mic and just speak freely. So int, strings, cars, doubles, floats, those are the big 5 or 6. And someone said structs. So these are kind of the main types. There's, you know, depending on your version of C and your level of comfort, right? There's, you know, there's short ints and there's long ints and there's unsigned ints and there may be bytes and things like that. And strings I'm going to sort of put in a separate category also. The real underlying data types in C are pretty few, right? Ints are, you know, usually 16 or 32 bits, depending on your processor, and they're just a weighted positional notation representation of an integer. Floats or doubles are, you know, usually IEEE 754 format, real numbers. And characters are short things. They're usually a single byte. But they also act like, you know, 8-bit ints that are unsigned and so on. But that's kind of it. right? And in all of those cases, you know, you have some collection of bytes, and you have individual bit values in those, and those get stored in memory. So when we study assembly language and microprocessors in 270, we're using a kind of peculiar processor. It's called a PIC processor. It's similar to an ARM architecture. It's fundamentally different from, say, an x86 architecture that we have in most of our machines, or we used to. And so the notion of memory locations is a little different in the PIC processor. We talk about file registers. But on something like, you know, a typical laptop computer, what do we have? We have our CPU. We have our memory. And the CPU, you know, specifies an address location in the memory, and the memory exchanges data with the CPU. So these addresses specify, you know, a certain location in the memory. So how many of you have actually, like, gone down to the hardware level in some way, shape, or form, looking at the actual memory of a computer? So I happen to be working on a pet project, so I'll show you a pretty sloppy example. It's mostly hidden by wires, but this is a simple CPU memory setup right here. This chip over here is a CPU chip. It's a 40-pin DIP, so it's like, you know, the chips you use in engineering 250 or 120 or 270. It's a 8-bit CPU. It's called a Z80. And this chip over here is a memory chip. And all the wires that you see going back and forth are how the CPU and the memory exchange information about addresses and data. So the part that's most relevant to us right now is this question of addressing our memory. Even though this is not how it's laid out in hardware, we really think of the memory as being 8 bits wide. Yeah, thanks. I tried to make my wires legible to some degree. Our memory is effectively 8 bits wide. Okay, now it's not. I mean, when you get a DRAM and you stick it in your computer and it's got all those little fingers, gold-plated contacts coming off the bottom, right? It's 32 or 64 or 128 or 256 bits wide, right? But functionally, when the CPU sends an instruction to the memory and it specifies an address, that address is referring to typically a location of an 8-bit quantity. So we're going to draw a lot of memory maps in this class. So let me start tagging this. We're going to start drawing a lot of memory maps in this class, and they're going to look kind of like this. So there's the memory. And we'll put addresses over here, and our addresses are sequential. And over here, we'll put the contents of each location of memory. These contents are 8 bits wide. All right. Now, question. C program integer x. How many bytes does an integer take on our Linux machine or your own Linux server at home? If you declare an integer, how many bytes is it? Or how many bits? And you can guess. 4 bytes, good. So So let's write some code. So I want to just write some code to make an integer and play around with the debugger and see what this thing looks like in memory. So there's some silly code. So we're going to set x equal to 12. All right. So if we print the value of x, it's 12. But let's see how x is organized in memory. Okay. So how can I find out where x is stored in memory? We know its value is 12 by just saying print 12. What could I do in GDB to find out the location where x is stored? Any ideas? Something with pointers, definitely. We're not going to use a find command. We're going to do this kind of like barehanded. But yeah, something with pointers. So what are the two things we keep bumping into with pointers? What are the funny symbols? Yeah, we've done this accidentally for sure. So what are the two symbols that put our nerves on edge when we see them in a C program because they mean we're dealing with pointers? Alright, so there's the arrow, there's the star, there's the ampersand. Alright, so we'll leave the arrow for now, but star and ampersand, right? Star x equals the thing pointed to by x. It's the thing at memory location x. Ampersand x equals the address of whatever this thing x is. Cool. Alright, so let's print ampersand x, and we get big, long, crazy hexadecimal number. Alright, this is the location where x is stored in memory. So let me make some notes on paper here, and we'll go back and forth. So the address of x equals, and I gotta count the f's once, 7FFF, FFFF. All right, and we know the value of x is 12, right? So, so let's examine that location in memory. Well, if we examine it, we see, you know, the value C in hex, which is 12. All right. But remember, I've just told you memory is byte oriented. It's really organized 8 bits at a time. And we're seeing more than 8 bits here. We're seeing a total of 8 hex digits. That's 32 bits. So let me examine the byte at location E37C. And at that byte, we find the value 0C. And at the next byte, we find a 0 and a 0 and a 0. All right, so let's use a more interesting value. So we'll put dead beef into x. And we'll go ahead and we're at the same location for x. That's good. So we'll go ahead and we'll give x a value. So that's dead beef in decimal. So now let's examine as a byte E37C. So let's see what's stored at that location in memory. And let's do it in hex. Alright, so at that location we find an EF. So let me make a memory map and then we'll take a look at it. So at this location we find EF. And then if I just hit enter, it'll show me the next location. So this is location E37D. And at that location we find BE. And then at location AD, or location 3, 7E, we find AD. And then at location 7F, we find DE. Dead beef is negative because D is bigger than 7. So it's got a leading 1, and since everything is 2's complement, an integer with a 1 in the most significant bit is negative. So that's why dead beef is negative. Alright, so here's what our memory map looks like, right? Now we said x equals this 32-bit quantity. But our memory is only 8 bits wide. So we found the address of x, it was this location, but this actual location can only store 8 bits. So which 8 bits of our 32-bit number gets stored? The 8 least significant bits. So this is the least significant byte. This is the most significant byte. Alright, so this is an exercise to just kind of like start playing around with thinking about how information is stored in the memory of a computer, because the computer is really just a bunch of bytes, one after another after another. And our memory addresses point to a byte. But we store things that are more interesting than bytes. We store integers, which are 32 bits. We store doubles, which are 64 bits, and have 3 different pieces to them: a sign bit, an exponent, and a mantissa. We store arrays, and pretty soon we store structures that have, 15 different components to them. And we're going to need to sometimes come back to the debugger and figure out how these things are stored in memory. So I want you to start thinking about this connection between the code we're writing in C and what's going on at the hardware level. Because it's going to be important. It's going to come up a lot, especially when we're debugging. When things aren't working as we expected, we're going to have to come down and look sometimes at the byte level. Now, the individual bytes, right, which are 8 bits, how are those stored? Well, this location in memory has 8 spots, and one of them is designated least significant bit, one is the most significant bit. And if this was, parallel RAM, there'd be 8 pins coming off of it that corresponded to those 8 bits. But then when you have things that are bigger than 8 bits, you got to figure out how you're going to wrap it in memory. Why is the least significant byte stored first and the most significant byte stored last? No reason. It's totally arbitrary. Yeah, it is surprising that everything stays in order and things don't get overwritten. When you're writing code for this course, and when you're doing like system programming courses, you will step on things all the time. You'll try to access something and it's actually stored somewhere else, so you access, random stuff, or you'll put 2 things in the same spot. Or you'll have one thing here and one thing there, but the first thing is a little bigger than you thought, and they'll overlap each other, and you get into all kinds of interesting things. And that makes debugging interesting. And because we're dealing with, sort of directly manipulating the memory at this low level, we'll find things like, code that works great in the debugger but breaks when it's not run in the debugger because things happen to be in different locations, and maybe the thing that we're overwriting doesn't get overwritten when we run this thing inside GDB because GDB organizes things differently, right, when we compile with a -G switch. And so we'll have bugs that come and go, or bugs that show up one day and don't show up the next day. And this is challenging, right? Getting good at debugging those kinds of situations is fantastic experience, right? That's stuff that's really useful. How can we keep track of what data can and can't be overwritten? Generally, if it's your data, you can do what you want with it. There's some ways that you can declare, strings, like if you make a string equal to double quote something, you can't change the value of that string on certain architectures, x86s, and GCC won't let you write a new value into those locations. But if you have memory that you mallocked, you can read it, you can write it, you can change it. That's all fine. So how does the operating system know what to overwrite? Well, so there's different levels, right? So within a program, you can have permission bits associated with blocks of memory, right? And if you have something that's critical code that should not be overwritten, you can actually write protect it. You can also read protect it if it's system information, or if it's memory that belongs to another process or another user. At the operating system level, it gets a little easier in some ways. So in terms of like files and stuff like that, that's all disk management, and it's a bunch of C code basically that keeps track of where things are, keeps track of what's available. With a running program in main memory, it's a little trickier because we don't really have a map of which memory locations we're using and which memory locations we're not, in some sense. So yeah, it is magic. That is the best answer, or just because. All right. So our processor least significant bytes are stored first if we have something that's longer than 8 bits. All right, and a lot of what we do is we deal with strings. And you probably remember well from your past that strings are actually character arrays. So we have an array of characters in this case. So here we have a character array S, and its address is FE300. So X was stored at FE2FC. And so X is 4 bytes, right? So it occupies locations 2FC, FD, FE, FF. And then the next location in memory would be E300, and that's where our array S starts. So now we can expand our memory map. And you notice our variable X changed location. So here's our memory. So these 4 locations, these 4 bytes, this is our integer x. That's the least significant byte. That's the most significant byte. And then this next chunk of locations is where S is stored. And this is S0, S1, and so on. Now this can get as complex as you want, right? You can keep digging into this. And if this is an array of characters, well, each character is a single byte. But if this was an array of integers, then S bracket 0 would take 4 bytes, which means this first location would be the least significant byte of S bracket 0. This would be the next byte, and then the most significant byte of S bracket 0. And then the 5th location would be the least significant byte of S bracket 1. And the 8th location would be the most significant byte of S bracket 1, and so on and so forth. If this is an array of pointers, like your argv array, right, pointers take either 4 or 8 bytes to store, depending on whether you're a 32 or 64-bit machine. And so this could be, you know, least significant byte, and the next 7 locations would be the other bytes going up to the most significant byte of that first address. Now the compiler keeps track of all of this for you. That's part of what the compiler's job is. When it changes your C source code into an executable, it's figuring this stuff out. It knows X takes 4 bytes, it figures out, okay, it's going to go right here, and it'll take 4 locations, and then the next location after that, I can use that for S, and that'll take 120 locations, because characters only take 1 byte. The compiler understands this. The linker, which is part of what GCC invokes, takes care of this for you. But since we're creating our own structures in memory, we're going to need to do some of this ourselves sometimes. And you kind of have to make peace with this, right? If you try to go through this course thinking, well, I'm not really going to worry about that part, I'll just stick to the C code, right? You're going to be constantly facing friction with your coding sessions. So you really got to, kind of like in 270 when I tell people, like, you've got to understand that you need to tell the CPU every single thing you want it to do. Kind of the same thing with data structures. You really got to embrace the fact that this is the level we're working at. And you're going to be spending time, you know, inside GDB dealing with this kind of stuff. But it's actually kind of a cool space to work in, because the more time you spend in that, the better you're going to understand what's going on. And when you can write a line of C code and have some part of your brain see what's happening, you know, to the bits and the memory and the control signals, that's a pretty powerful way to code. So yeah, drink your Kool-Aid. All right, so let's talk about structs. So somebody mentioned struct as a data type, and it is, and it's the main data type we're going to use. We're going to write a lot of our own structures. So, so what's the idea of a structure? Let's think about arrays. So suppose we want to, you know, read a set of scores, save those scores in memory, and then pass that set of data to a function to calculate stats, and then pass that to a function to print a report. All right, so we want to write a C program that, you know, lets you type in scores from some test one at a time, saves them in an array, and then we want to pass that array to some functions and do some stuff with it. So this is not, you know, different from things you did in 224. You make an array, you have a initial counter that's set to 0. You get an input score somehow, use fgets and scanf or whatever. You save it in the array at the location given by your counter, and then you increment your counter. And if you type in 5 scores, right, you've got 5 locations in your array filled. If you type in 50 scores, you've got 50 locations in your array filled. Now, when you pass that array to a function, so let's make a function called calculate, right? We pass in this array of scores. We declare it down here in our calculate function as just a pointer to an integer, right? Because arrays are pointers. But inside our calculate function, let's say we want to calculate the average. So we have to, add up all of the scores and then divide by the number of the scores. What's the piece of information that's missing here? What's the other piece of information we need to be able to add up all of the scores and calculate the average? How many scores do you have? Yes. We don't know the size of the array. And just passing a pointer to an integer does not tell us how big the array is. Because what happens when you pass a pointer to an integer, you get the address of this first entry. If S was my array of scores and, S was stored here, I'm actually calling this function with an integer argument, which is, 7FFF300, the address of this first entry. And I can look at that location and be pretty sure I'm going to see an integer. And I can go 4 bytes later and look at the next 4 locations and see another integer. But there's nothing in here that tells me you've got 5 integers to look at. Right? There is no inherent length to an array in C. So I could, if I knew the address of the last piece of the array, I could pass that to my calculate function. But just looking at this array, which is really just an address in memory, there's nothing that tells me the address of the last piece of the array either. And this is just the nature of C, right? I mean, this is how things work in assembly language, and C is basically high-level assembly. Now, we could do a trick, right? We could store a -1 as a bogus score after our last valid score, and then we could iterate through here, maybe with a for loop or something, and go until we see a score that's equal to -1, and then we'd know that was the end of our array. So we could do that, right? And we do this with strings. With strings, this works because strings were, originally designed to store ASCII character codes, and ASCII character code 0 doesn't represent a printable character. So it was pretty safe to say, you can make an array of characters, and at the end of that array, just store a 0. That's the null terminator. And now, all you need to know is the address where the string starts, and you just start looking through until you find a 0, and you say, okay, everything up to that point, that's my string. So that works great. But the problem is with integers, there's no magic value of an integer that we can use to say, okay, this is the end of the array. Maybe for certain cases like scores, we could say, well, you can't have a negative score, so -1 marks the end of the array. But if this is just arbitrary integer data, there's no reserved value that we can use to say this is not part of our array, this is a marker. So we have this problem that we don't have an inherent size. So we have to pass another integer, which is the length of the array. Well, once we have that, we're golden, right? We can loop through from 0 to length -1. We can add up to a running sum, and then we can divide by length. And if length is 0, we can do something and say there's no data, and so on. But we find that once we have an array of integers, we're constantly passing around, this array itself plus its length. All right, so this is a motivation for using a structure statement. So a structure statement lets us create a new type of variable that contains more than one piece of information. So here's what we could do. We could say structure scores. And then we list what the types of pieces of information are, what we call the fields of this structure. So we can have an array of integers that we call grades, and we can have an integer which is the length. So this is the array of scores, and this is the number of entries in this array. Now there's different ways you could do this. You could make length the index of the last entry in your scores array, in your grades array. Or you could make it the actual number of entries, or you could, code it up with some other, representation. You could make it 1 for 10 scores and a 2 for 20 scores, or, whatever. It's up to you, okay? But here's a pretty straightforward way to do it. Just a structure with two pieces to it, two fields, an array of grades, and an integer that tells me how big that array is. And when we say things like how big the array is, that's a bit of a misnomer, right? Arrays don't have an inherent size. So when I say how big the array is, I mean how much meaningful information do we find in that array? So we make this statement, and it creates basically a new type of variable for us called a struct scores. And now I can say struct scores S if I want a lazy variable name. And S is now this new type of variable that has two pieces to it. Once I've made this declaration, I can say S dot grades, or I can say S dot length. And S dot grades is a pointer to an integer. It's an array of ints. And S dot length is an integer. So now I could call my calculate function and just pass it S. And inside my calculate function, the argument that I pick up will be declared to be an object of type struct scores, and I can use that variable name dot grades or dot length to pick up those fields. All right, is this making sense? What does the dot do? So the dot says, yeah, access part of the structure. So if S is a structure, S dot some field name says, give me that piece of the structure. And that's just C syntax. So yeah, you could definitely do this with a pair of variables. You could have the array itself, and you could have a length, right? This really just combines those two pieces of data into a new type of data, which is called a struct scores. But it's not fundamentally doing something you couldn't do in a different way. And when this is compiled down to assembly language, right, there's no structures, there's no arrays. It's just, machine code. And machine code doesn't understand these constructs, and so, you could always do this by writing machine code in C. But it's a simplification. And it's an important simplification because not only does it make our code cleaner, but it makes it less error prone in some ways. All right, and this is all preamble for CSE223. When we start talking about object-oriented programming, objects are really structures, kind of amped up. All right, and you've done this in 121, and we've maybe talked about it a little in 224. But we'll be working extensively with structures in this course. All right. Let's see. Should we write code or should we talk more? We got 9 minutes. 223 we use Java. So we talk about C++ a little bit sometimes, depending on the mood and the timing. But we use Java for our object-oriented class. Same thing, basically. Same ideas. Once you know one object-oriented language, you're kind of good to switch to whatever. Just like, you know, if you know C, you can go ahead and do other non-object languages. Yeah, no ODP today. Might post one at the end of the week. But end of the week, we'll talk about programming assignment 1, which will involve structures and arrays of structures. And then I'll start pushing out some ODPs next week to go along with those. All right, I kind of want to write code. I won't write code. So if we were to do this in a really simple way, we might do something like this. Inside this score structure, we could declare grades to be an array of 120 integers. And that would mean we could have up to 120 scores in this structure, but length would still tell us how many of those 120 potential scores actually exist, how many of those locations in this array are relevant. And we're assuming that the scores start with element 0 in the grades array and go one right after another. All right, so the first score would be grade 0, the next one grades 1, next one grades 2. If we have a total of 5 scores according to length, those would be in grades elements 0, 1, 2, 3, and 4. All right, now that's not always going to be the case. But for now, we'll just assume that, you know, these grades are packed starting at the beginning of the array, and they go up through element length minus 1. And so in that case, you know, we don't have to do any extra initialization. We can just declare an object of type struct scores. And bingo, if we looked at S in memory, it would point to somewhere where there were 120 integers allocated, and there would be 4 bytes allocated for the length. And how are those set up? It's up to the compiler and the linker. It may not be that the grades are stored before the length. They could be stored after. So yeah, let's go ahead and write some code for that. Didn't see anything. That ending semicolon is important. I'm just going to put some statements here so I can step into the beginning of the executable code. Yeah, good question. Someone asked, why does compiled code look like that and not ones and zeros? Well, what I did was I VI'd M1. M1 is an executable program, right? But VI, what does VI do? It looks at the ones and zeros in a file and it translates them into ASCII and displays those. So M1.C is ones and zeros on my hard drive, but if I VI it, it finds, you know, ones and zeros corresponding to the ASCII code for a lowercase s, and it displays a lowercase s. And so if I VI M1, even though it's a binary file, I see printable stuff. If I have you know, a bit pattern of all zeros, VI will display that as a caret followed by an @ sign. That's how it renders ASCII code 0. Caret followed by a question mark is, I believe, ASCII code 127 or 255. And then ELF happen to be, you know, ASCII codes that correspond to printable characters, so it prints those out. So when you see something like this, right, you're definitely looking at a binary file. And if I just cat it, I can mess up my terminal a little bit sometimes. Sometimes it'll change color, things like that. If I do XXD M1 and put it into more, now I can look at it in a more controlled way. I can see that my first byte is 7F, right, which printed as a caret question mark, but here it just prints out as a dot saying it's not a printable character. And then there's my ELF right there, so 45, 4C, and 46. There's a 02, 01, 01, and then a bunch of nulls, and those all just print out as dots. So XXD is a nice utility to look at binary files. But if I XXD M1.C, right, same thing. We can see byte for byte the in this case hexadecimal ASCII code, but these are mostly printable characters, and so we see them translated over here. Well, what's this last one over here? Is 0A? That's a new line, so that prints as a dot, and then 20 is a space. So this is a really useful tool when you're trying to work with binary data. XXD or OD for octal dump are good ones. Another good one is strings, that pulls out the printable strings of a certain minimum length and just shows you those. So if I strings my executable file, I get the stuff that's human readable. And you know, it was compiled with a -G switch, so it has lots of information inside here to help with debugging. Alright, so let's compile up our structure code. We have 2 minutes and 3 seconds. That's plenty of time. Alright, so we'll step into here. So let's print out what was our structure. Scores S. Okay, so if we print out S, it shows us, you know, because it's GDB and it understands our source code, if I print out S, it shows us it's an array of grades, and there's all the grades, and, you know, they're basically random. And then our length, which is also random, which is -7072. Right, so this is uninitialized data. This is why you want to make sure you initialize stuff, right? And probably all I need to initialize is length. Because if I set length to 0, hopefully my code's not looking at any of this data. But let's see where S is stored. So let's print the address of S. And it's stored at E190. Alright. Let's print the address of S.grades. So grades are stored at E190. So that's the beginning of our structure. And if I print the address of S.length, that's stored at location E370. So if you add this up, if you take 120 bytes times 4 bytes per integer and add that to this address, you should get that address. So you could make a map of this, and you would find that at the beginning of your structure you have your array, 120 bytes, followed by the 4 bytes of the length. So there's a GDB quiz posted, and that quiz, I think it's due in February, double check. But that's basically an exercise in playing around with GDB and looking at structures in the debugger and getting some practice with this. So we'll be doing this a lot. But anyway, that's the basic setup for structures, right? Taking multiple types of data, putting them together into a single composite structure. Yeah, hopefully these aren't actual grades, except for this person. And this actually, this isn't a bad grade either. So yeah. All right, cool. So have a good afternoon. I will see you tomorrow. Tomorrow we will start digging into how how structures relate to efficiency of operations. All right, I will see you tomorrow.